Okay, let's talk a little bit about the element mass matrices very briefly. And this is important. It's kind of like the stiffness, what we've done there for the structural problem in quasi-static. So since the shape functions for various elements have been discussed in detail, we can also present the element mass matrices. So you treat the material density to be constant over the element, and we're left with this mass of the element is equal to rho times the integral of these shape functions, n transpose n dv. So for the one-dimensional bar, we know that we have n1 and n2, right? And those look like something like this. So we write that in isoparametric form, like we've done all before. So we have integral going from -1 to the 1 over the master element, and we integrate those shape functions. Okay. So you end up with element mass matrix for the 1D bar like this. And then this would have to be assembled. Okay, so it's a very similar procedure. We get a different looking result, but it's a similar procedure with the stiffness. For the constant strain element, we have different N matrix, right? But we do the same formula basically, and you end up with something like this. Okay, so there's constant values, and it looks different. We have more things, and then again, it has to be assembled. For the quadrilateral element, it's a little more tricky because, again, we have a different n. We plug it into that equation. Our n now depends on those psi and eta terms, right? So we have to, again, perform numerical integration when we do the mass matrices. So the procedure is very similar to what we have done in stiffness, except for this is mass now. So the next thing we want to look at is just some solution methods for the vibrational problem.